June 19, 44, Normandy. A Panther tank sits on the side of a dirt road near Villers-Bocage. Its engine is running. The crew is not under fire. There are no Allied aircraft overhead. There are no Sherman tanks on the horizon. The Panther is not moving because it cannot. Its final drive has ceased. The crew has been there for 6 hours. A recovery vehicle is coming. Eventually. The tank, worth 450,000 Reichsmarks and 6 months of a skilled worker's labor, is a 200,000-pound roadblock. This was not an isolated incident. By the end of the Normandy campaign, more than 80% of Panther losses were not caused by Allied guns, airstrikes, or Firefly 17-pounders. They were caused by a single mechanical component, undersized by exactly 10 millimeters. In the summer of 1943, Germany unveiled what it believed was the definitive answer to Allied armor superiority, the Panzer V, the Panther. On paper, it was extraordinary. The 75mm KWK-42 L-70 cannon could penetrate 140 millimeters of vertical armor at 1,000 meters. At that range, it could kill a Sherman at any angle. It could kill a T-34-85 frontally. At reduced ranges, it could penetrate an IS-2. The frontal hull armor was 80 millimeters, sloped at 55 degrees. Effective protection equivalent, approximately 140 millimeters of vertical plate. No standard Allied anti-tank weapon of 1944 could penetrate it from the front at any practical combat range. The turret face, 100 millimeters. The gun mantlet, 110 millimeters. Wehrmacht ordnance assessments were unambiguous. The Panther was not merely superior to anything the Allies had in France. It was qualitatively superior to almost everything on the Eastern Front as well. And battlefield results confirmed the theory. In individual engagements, Panther crews were destroying Allied armor at ratios of 5-1, 8-1, sometimes higher. A single Panther in a prepared defensive position could hold a road junction against an entire Allied armored company for hours. The British discovered this at Villers-Bocage on June 13, 1944. In the space of 2 hours, one Tiger and its supporting Panthers destroyed 25 Allied vehicles on a single road. The junction held. German command drew the logical conclusion. Qualitative superiority compensates for numerical inferiority. One Panther could replace 3 Shermans. That was the operational strategy for Normandy, and it was built on a foundation that was already failing, not under Allied fire, but under its own weight. To understand what destroyed the Panther in Normandy, you must understand one component, one assembly, hidden inside the lower hull, behind the drive sprockets, invisible from the outside, the Seitenvorgelege, the final drive. In a tank, the engine produces rotational power. The transmission manages gear ratios, high ratios for speed, low ratios for torque. But the transmission cannot connect directly to the sprockets that drive the tracks. The torque loads are too high. The rotational speeds are too different. The final drive is the last mechanical link between the engine and the track. A set of reduction gears, in the Panther's case, a planetary gear set, that multiplies torque one final time before it reaches the sprocket. Here is the analogy. Think of a bicycle. When you climb a steep hill in low gear, your legs spin fast to move slowly. You are trading rotational speed for force. The final drive of a tank does exactly this, at a scale that is difficult to comprehend. It takes high-speed, moderate torque rotation from the transmission and converts it into low-speed, extremely high-torque rotation at the sprocket. On a 45-ton vehicle, the forces on every gear tooth in that final reduction stage are measured not in kilograms, but in metric tons, applied with every single rotation. Every second the tank is moving. Now here is the problem. The Panther's final drive was not designed for a 45-ton tank. It was designed for a 25-ton tank. When the Panther project began in 1941, the specifications called for a vehicle in the 30 to 35-ton range. The final drive, the Seitenvorgelege, was designed and prototyped accordingly. Engineers at Maschinenfabrik Augsburg-Nürnberg built a system that could handle the torque loads of a 35-ton vehicle operating in European terrain. Then the Panther grew. 80 millimeters of sloped frontal armor, a heavier, longer gun, reinforced suspension to carry the load, additional crew, and combat equipment. By the time the Panther entered production in January 1943, the vehicle weighed 44.8 tons. The final drive housing was never fundamentally redesigned. The gear tooth dimensions were never recalculated for the new weight class. The planetary gear set that was adequate for 35 tons was now carrying 45 tons, a 28% increase in mass, with proportionally higher torque loads on every gear tooth. every revolution, and the engineers knew it. In April 1943, 2 months before Kursk, Heinz Guderian, Inspector General of Armored Troops, received a technical report from Wehrmacht weapons testing, the WWII SEX. The report noted that the Panther's final drive showed, and I quote, accelerated wear under sustained high torque operation, and recommended redesign of the final drive housing with increased gear face width. Production had already begun. There were delivery schedules. There was political pressure. Hitler wanted Panthers at Kursk. The final drive was not redesigned. To understand exactly why the final drive failed, you need to understand a principle from contact mechanics called Hertzian contact stress. It sounds technical. The concept is not. When two curved surfaces press against each other, like two gear teeth engaging, they do not contact along a wide, flat area. They contact along an extremely small surface, a sliver, a tiny ellipse measured in fractions of a millimeter. All the force between those two teeth is concentrated in that tiny area. Here is the analogy. Take a ballpoint pen, press the tip against the back of your hand. You feel pressure, manageable. Now take that same force and concentrate it onto the tip of a needle. Same force, 1,000 times smaller contact area. The needle breaks the skin. That is Hertzian contact stress. The smaller the contact area, the higher the pressure per unit of surface. And the higher the pressure, the faster the material fails. In the Panther's final drive, under full combat load, 44.8 tons, bocage terrain, repeated low-speed turns, the Hertzian contact stress at the gear tooth surface exceeded a specific threshold. That threshold is called the endurance limit of the material. Below the endurance limit, steel can be cyclically stressed, loaded and unloaded, indefinitely. The structure remains intact. Above the endurance limit, something different happens. Microscopic cracks begin forming in the subsurface of the gear tooth. Not on the surface, beneath it. Each loading cycle propagates those cracks fractionally further. You cannot see them. The tank operates normally. Nothing in the driver's controls indicates a problem. Until the cracks reach a critical depth. Then, in the space of seconds, sometimes a few seconds of sustained high-torque cornering, the tooth surface spalls. Contact fatigue failure. A fragment of the gear tooth breaks away. That fragment circulates through the gear oil. It is harder than the oil, but softer than the gears it is now grinding. The remaining teeth, already weakened by their own subsurface cracks, begin failing in cascade. Within minutes, the final drive ceases. The Panther stops. Now, here is the specific engineering parameter that was wrong. The face width. In gear design, face width is the depth of the gear tooth measured along the rotational axis. A wider face means a larger contact area between meshing teeth. A larger contact area means lower Hertzian stress per unit of surface. Lower stress means longer fatigue life. For the Panther's weight class, a vehicle of 45 tons operating in high-torque off-road conditions, engineering calculations required a final drive gear face width of approximately 65 millimeters. The actual face width in the production Seitenvorgelege was 55 millimeters, 10 millimeters of missing metal. In a 45-ton weapon system, that gap between what the engineering required and what was produced was the difference between a functional war machine and a scheduled breakdown, and Normandy made it catastrophically worse. The bocage, the hedgerow country of the Norman interior, earthen embankments, ancient and dense, dividing the landscape into compartments rarely wider than 50 meters, roads narrow enough that a Panther could barely fit without its track overhangs scraping the embankments on both sides. Maneuvering in the bocage meant something very specific in engineering terms: constant sharp turns at low speed, under high throttle. These are exactly the conditions that maximize torque load on the final drive. A Panther crossing open Russian steppe could travel in relatively straight lines for kilometers. The final drive operated at consistent loads. Heat dissipated through the gear oil. Stress cycles were uniform. A Panther in Normandy turned constantly. Every turn required one track to accelerate while the other braked or reversed, applying asymmetrical pulsed torque shock loads directly through the final drive differential. Each turn was a stress spike into gear teeth that were already operating above their endurance limit. The documented mean distance between failures for the Panther's final drive in bocage conditions was approximately 150 kilometers. 150 kilometers. A distance that any modern passenger vehicle covers without a second thought. A distance that a Sherman M4, with its Continental R 975 radial engine and its heavier, but more conservatively engineered drivetrain, could cover with routine oil changes. and replacing a Panther final drive in field conditions? With a trained crew and proper equipment, the minimum time was 6 hours. In reality, without a dedicated recovery vehicle, without a crane capable of lifting the final drive assembly, which weighed approximately 340 kilograms, the realistic repair time was 12 to 16 hours. By which time, in the mobile warfare of Normandy, the tactical situation had usually changed entirely. Now the numbers. Panzerlehr Division's Armored Regiment entered Normandy on June 6, 1944, with 89 operational Panthers. This was one of the best-equipped, best-trained Panzer divisions in the German order of battle. Panzerlehr's tankers were instructors, men who had spent years teaching other crews how to fight armored warfare. By July 24, 1944, 48 days later, operational strength was 14 Panthers. 14 of the 75 Panthers that were non-operational, combat losses from Allied fire account for fewer than 25%. Wehrmacht maintenance records classify the remaining 75% as mechanical breakdowns. Final drive failure is listed as the primary cause. In that same period, American factories were producing approximately 400 Sherman tanks per month. British depots were receiving replacement vehicles at a rate that allowed complete reconstitution of all Normandy armored losses within 60 days. Germany's total Panther production in the summer of 1944 was approximately 330 units per month, allocated across the Western Front, the Eastern Front, and Italy simultaneously. Final drive failures in Normandy alone were consuming Panthers faster than the factories in Bavaria could build them. But the industrial arithmetic only partially captures what failed. The deeper failure is structural. Every Sherman that broke down could be repaired in hours, using standardized components available at any Allied forward depot. Every Sherman that was destroyed could be replaced within weeks from a production system operating without interruption, thousands of kilometers from any battlefield. Every Panther that broke down required specialized parts that were perpetually on back order. Every Panther that was destroyed came from a production allocation already divided among 3 simultaneous fronts, with no industrial reserve. The Panther was tactically superior. In a prepared defensive position with a trained crew, there was no Allied tank that could engage it on equal terms at range. That is historically accurate and not in dispute, but tactics are temporary. Logistics is permanent. Heinz Guderian, the architect of Germany's armored force, the man who had fought for the Panther against institutional resistance, who had warned against deploying it at Kursk before the drivetrain issues were resolved, wrote in his memoir, Panzer Leader, published in 1950, "The bravery and skill of the Panther crews cannot compensate for mechanical deficiencies that were known, documented, and left uncorrected. A weapon that cannot reach the battle is no weapon at all." He was not speaking of the cannon. He was not speaking of the armor. He was speaking of 10 millimeters of gear tooth face width. Germany built the most sophisticated individual tank of World War II and destroyed its operational effectiveness with an engineering calculation error that every technician in the program already knew about. The Seitenvorgelege was not a secret. It was not a surprise. It was a documented, measured, quantified deficiency present in every single Panther that entered France in June 1944. And it killed more Panthers in Normandy than the Firefly, the Typhoon, and the American artillery combined. That is not the story of Allied industrial power overwhelming German ingenuity. That is the story of a decision made under political pressure in a production system that had lost the ability to stop and fix what it already knew was broken, that cost Germany the armored campaign in the West before the first Panther reached the bocage. If the engineering behind these failures changes how you see the Panther, if you want to understand the technical decisions that actually decided World War II, you know what to do. Subscribe. Because the next story is just as specific, just as technical, and just as surprising.